You're given the following block diagram. What is the natural frequency and damping ratio of the open loop system? This is gonna go fast because this is a review, but I'll do more videos on the reasoning behind it. So here we have S plus 5 times S plus 6 equals 0. This is our characteristic equation. What we're going to do is we're going to multiply it out. Is equal to 0. Then we're going to recognize that this is the natural frequency. This is omega n. So omega n is equal to the square root of 30 radians per second. Now the square root of 30 radians per second is, let me figure that out real quick. Square root of 30, 5.477. So that would be 5.477 radians per second. Now what we want to do, they also asked us for the natural frequency, that's what we just found, the damping ratio. So damping ratio with this letter, well, it's actually not this letter. Let's see if I can do it. I know I like that better, even though it's really not this letter. This is going to be equal to this number, 11, divided by 2 times our natural frequency, just the square root of 30. It's going to be unitless. So that's going to be 11 divided by 2 times the square root of 30, which is 1.00, about 1.004. Okay, now that takes care of part A. Part B is form the closed loop transfer function. So the closed loop transfer function is equal to GH over 1 plus GH. So the closed loop transfer function is equal to GH over 1 plus GH, where this path is H, this is H, and the forward path, it's called forward path because we're going forward. I guess the right is considered forward, although you can be left and still go forward. And so how are we going to do this? Well, what's our G? Well, our G is what I said over there. So we're going to have S plus 3, all of it divided by, and I need more space. So S plus 3, all of it divided by S plus 5 and S plus 6, S plus 5, S plus 6, all of that we divide by 1 plus, and now we have, so that was just G. Now if we multiply it by H, and we're including K in this case, wait, G over 1 plus GH. I think I wrote the equation wrong. I meant to write just G, but let me double check on the book. This is the magic formula. So this one, you should really just memorize it. And for some reason, I'm having a little bit of confusion. It's G over 1 plus G. So my bad for that. It's just going to be this one. So I don't have a K in there because it's not in my forward path. But I have that same thing, S plus 3 divided by S plus 5 times S plus, let me do it again, s plus 5 times s plus 6, and now we have a k in there as well. So now that we have this, we can multiply this, the numerator and the denominator, by the same thing, and we won't change the fraction. So why don't we do something interesting and multiply, and I don't want this to be smaller, and we multiply by s plus 5 and s plus 6. And remember, as long as I do it on the top and on the bottom, it's really just multiplying by 1 over 1. So, why would that be interesting? Well, you would notice that this cancels. So at the top, we can just write s plus 3. At the bottom, this has to be distributed. Don't make that mistake. So that's going to be s plus 5 times s plus 6 plus s plus 3 times our k. Just like that. And now that we have this, this is our closed loop transfer function. Now we can even multiply this further. So let's say we do that. So here, at the top, we're just gonna have s plus 3. I'm trying to write neat. Okay. Now let's develop that part. So we'll have an s squared. I know the pattern, otherwise you have to FOIL it out. And then we'll have 5 times s plus 6 times s, which is 11s plus 11 times s plus 6 times 5, which is 30, which is what we had before. And now we have plus k times s plus 3 times k. And now that we have this, what are we going to do? So now I can take the s's and group them out, group the coefficients. So we have an s squared plus 11 plus k multiplied by s plus 30 plus 3 times k. And here we're going to have an s plus 3. And this is it. Let me see if I made any mistake. No, this is right. This is my third term here. And now let's see for c. At k equals 0, what is the characteristic equation? So let k be 0. Now if k is 0, we don't have a closed loop. So that would be s plus 3. Well, sorry, I just want the bottom. So we'll have s squared plus 11. I'm going to say I substitute 0 here with the yellow. So we're going to have 11 plus, oh, sorry. I just want to show you where it's coming from. So we're putting it here. 11 plus 0 times s plus 30 plus 3 times 0. And we close that as well. We set that equal to 0. So what are we going to do now? We're going to do s squared plus 11s plus 30, and that's equal to 0, which is what we had originally, right? This is our original characteristic equation, which makes sense. Original characteristic equation. Okay, so now what we're going to do is we're going to do d. What is d going to be? What are the poles and zeros of the open loop system? So we want to know the poles and zeros of the open loop system. So we just have to look here, and I'll write it again over here for you. So s plus 3 divided by s plus 5 and s plus 6. S plus 5 and s plus 6. So the zeros are what makes this expression zeros. So the zeros are just -3, because if I put -3 here, I'm going to get 0. Now the poles are what makes this basically undefined. So what makes zeros in the denominator? So -5 and -6. Just like that. Sketch the open loop poles and the zeros on the complex plane. So if we take a plane, oh, how do I do this? I only want the left part, and I'm going to bring it over. I guess I'll do it here. No, maybe we should do it over here. Okay, and this is going to be part E. So for part E, it says, okay, sketch them. So the zeros, we're going to indicate them with a 0. So let's say that this is a 0, and let's say this is -3, and then a -5 and -6 we have poles. The poles will do with the crosses, so -5, and this is not to scale, -6. And then we would label our axis. This is the imaginary axis, and this is the real axis. Okay, so this was it for problem 8.1. Hope you enjoyed it, and I'll see you next time.